So we're now moving from the science of the National Science Foundation to that of the NASA. John Grunsfeld is a physicist. He has a degree in physics, but he is also a well-known astronaut. As a matter of fact, he has flown in 5 space shuttle flights, 3 of which service the Hubble Space Telescope. And so we are very happy that he could come and tell us his view about how NASA can, over the next decade or so, address some of the big science questions with big projects. Thank you.
Thank you very much, and thank you, Francis, for setting up various bits of my talk once the little swirling wheel lets me have access to it. But it's really a pleasure to talk to you about not just what goes on in a square kilometer under the ice in Antarctica, but the rest of the universe and where those cosmic sources are, but also about the Earth. And hopefully in a moment here, I'll have access to it. Yes. All right, so rather than talk too much about policy, what I want to do is tell you a little bit about what science we do at NASA. And I want to start with a mission statement, which is, what I think about every day when I come to work. And I can't help but put a Hubble picture. This is a picture that my spacewalking partner Drew Feustel and other physicists took of the Earth and the shuttle payload bay, and inside of that spacesuit is me. But our mission is to innovate, explore, discover, and inspire. And that innovation covers the technology that we invent, that we build, and by we, I mean NASA, the scientific community, the engineering community. And we build these things so that we can explore. And we explore the Earth, we explore the solar system, we explore the Sun-Earth connection, and of course the rest of the universe. And when we all explore, and this is what all of you do, we discover things. And I'm convinced that that's genetically programmed. And when we discover things and we share it with the public, we inspire. Now, this is going to be a very long list of big scientific questions that NASA has to address. Where did we come from? Where are we going? And are we alone? And again, this is my very simplistic way of thinking about why we do the science that we do. And to answer this, we've drawn kind of a diagram that connects all the different scientific disciplines. And essentially, the questions we're trying to ask is, from the very earliest moments of the Big Bang, how do we connect the events that happened in the early inflationary universe to when light and matter finally became disconnected? We emerged from the dark ages, the first stars, galaxies formed, the evolution of the cosmos, all of its constituents lead to an amazing planet like Earth. And can we understand the Earth well enough? Can we understand the natural cycles, the anthropogenic cycles well enough to be able to predict the future? And for me, there's sort of 2 driving questions. Are we alone? Is there life outside of planet Earth? It seems like compelling, but as scientists, we actually want proof. And is human life sustainable on Earth? Which may be related to the are we alone question through Fermi paradox or Drake equation. I won't talk about that today. What's truly incredible is that using ground-based telescopes, radio astronomy, optical telescopes, neutrino telescopes, perhaps, and small telescopes orbiting the Earth and in space, we've been able to put together a story that starts in those earliest moments of the Big Bang, our first impressions of that through the Cosmic Background Explorer, through Wilkinson Microwave Anisotropy Probe, through Planck, the imprint of that Big Bang. There's a little gap when basically light didn't propagate through the dense hydrogen in the universe. And then with Hubble, we start seeing the emergence of some of the toddler galaxies, not baby galaxies, not baby stars, but toddler galaxies as they were about 13 billion years ago. And then for the rest of the 13 billion year history of the universe, we're able to map out the history of the universe, the evolution, the collision of galaxies, the birth of solar systems, of stars, the death of stars, all the way up into the emergence of solar systems. ALMA is a huge tool that's brought online now to be able to help us explore that, as well as the Spitzer telescope and Hubble and others. And now we're trying to understand how the Earth works as well in our solar system. It's an incredible story with great detail that we've been able to put together, truly remarkable. Now, we could map our big questions into very detailed ones. I won't go through all of those. I've talked about some. But on Earth science, we really want to be able to understand the natural underlying cycles. And we know the Earth's atmosphere has always been changing. The climate has always been changing. We know that life has had a significant impact on the Earth for at least the last 700 million years, probably much longer. For the last 3.5 billion years, life has changed the geology of the Earth. But how are we changing it? We need to understand the underlying physical, natural cycles first. In heliophysics, of course, all of terrestrial weather is easy, right? Because it's caused by the rotation of the Earth and the input of the sun. Maybe a little chemistry. Should be a simple problem. It's a very hard problem. Understanding what causes the sun to vary, even harder. Of course, that sun is a background neutrino source, as we just heard. And I'll show you a picture of that. Planetary science. It's a little bit like biology, but we're trying to understand how did our solar system come to be the way that it is. And when Hubble was launched, we knew about one solar system with 9 planets. Then it was demoted to 8 planets. But now we know about thousands of other solar systems. In fact, when you look at the night sky, virtually every star you see has a solar system around it, and a significant fraction, maybe a fifth, have something like Earth around it. We want to understand those, the realm of astrophysics and the rest of the universe. How did the chemical elements form? We know a great deal about that. How are they cycled through galaxies, through stars, to be able to build up all of the heavy elements that make up us? What are those other solar systems like? How common are Earths? How common are Earth's inhabitable zones? What's the atmospheric constitution? What are dark matter and dark energy? Now, that last one, of course, everything I told you about that story accounts for the 4% of the universe, well, the 2% we actually see. Everything else is pretty much unknown. So it's still a lot to do. Policy-wise, what we do is we try and map that into a connection diagram that contains all of those elements. And the size of these is not important. It's just that there's 2 boundary conditions. Cosmology the Big Bang, origin of evolution of life, representing those endpoints. And in between, there's lots of different boxes that are research areas. And then each of those boxes gets broken down. And we want to try and provide funding that balances all of these areas so that we can understand the whole story and not leave out major chapters. Now, to do that, you need accountants. And the accountants are both at NASA and in Congress. And they budget for our science in 4 major bins. Heliophysics, the study of the sun and the sun-Earth connection, magnetically speaking. Earth science, the study of how the Earth system works. Planetary science, and astrophysics. But of course, these are all connected because, after all, the sun is a star, the Earth is a planet. Planets, our solar system is just one of many. So in the end, it's all astrophysics. Of course, that's a personal bias. But it is an integrated program of science. So I'm going to spend the next 3 hours going through our entire fleet of satellites. And this is how we do it. We fly missions. We fly satellites. We fly aircraft. We do ground experiments to try and understand how the physics works, how the systems work. And I'll just suffice it to say that we operate 97 independent missions, 124 spacecraft. Last year, we had 8 high-altitude balloon launches. In fact, we have a balloon up right now that's circling the globe. It's a super-pressure balloon that could give us months of exposure for cosmic ray experiments, astrophysics, heliophysics. 12 sounding rockets. These go anywhere from 100 kilometers to 1,400 kilometers, and 4,600 airborne hours, both for Earth science and including our SOFIA Airborne Observatory, infrared observatory. So I thought I'd just show a few fun things. This is the neutrino source you heard about from Francis. It's always amazing to me that we live right next to this amazing star, and the plasma physics, the magnetohydrodynamics, the nuclear physics is all there for us to learn. Yet from the time we're little, what do our parents tell us? Don't look at the sun. So we have a whole field that is launching satellites. In fact, we just launched the multi-scale magnetospheric mission, MMS, which is going to study magnetic reconnection in the Earth's magnetosphere, something that still is not very well understood, but applies to everything that Francis was talking about around black holes, pulsars, massive black holes and galactic centers, fundamental process in physics that we're still trying to understand, that we can see in the sun, that we can see around Earth. We have the Van Allen probes also circling the Earth, trying to understand the magnetosphere, the stereo spacecraft looking at the sun from 2 different angles. This happens to be the Solar Dynamics Observatory, which generates terabytes of data observing the sun in great detail. And when there's a large coronal mass ejection, these are little coronal loops. It's just fantastic to see, and there's even iPhone apps so that you can see it in near real time. Stereo spacecraft are on the other side of the sun now, so we can't talk to them. We just launched the Discover Space Weather Satellite for NOAA, so lots going on. And we have some very big strategic missions coming up, including Solar Probe Plus, which is the first real mission to the sun. It's going to go within about 9 solar radii from the sun. We're going to go at night. But actually, it has an amazing heat shield to protect all the instruments, and they're just sort of poking around the edge. Really phenomenal that it's able to do that. Now, in school, we all learned about the hydrologic cycle. How hard can it be? It rains, the rain falls on land, it runs through rivers into the ocean evaporates back into clouds, some of it's in ice. In fact, we need to finish that important neutrino work before all the ice is gone in Antarctica. Fortunately, we have quite a while to worry about that. Unfortunately, it's probably not there for forever, nor has it been, of course. There's fossils in the Transantarctic mountains indicating that it was once quite warm and wet. But understanding this water cycle is actually pretty important and rather difficult. So to do that, we have the perspective from space with our Earth science satellites, and it really takes that synoptic whole Earth view to understand the whole story. And let me just give you one example. Sea level rise. Now, sea level rise doesn't rise everywhere the same because of the underlying topography of the oceans, some places more than others. So this is a mean sea level rise. And it's amazing that since we've been measuring it with laser and radar altimetry from 1993 to the present, it's a pretty monotonic rise of about 3.2 millimeters per year. But we also have 2 satellites that are flying over the globe in formation, and it's measuring the gravity field of the Earth, very high multipole order, such that simply said, if you fly over something massive, the first satellite gets accelerated a little bit, and then it goes past, the second satellite gets accelerated. They basically fly in formation. If you measure the distance between them, you can measure how much mass is below you. So we can also measure the change in ocean mass. If sea level's going up, then water should be going into the oceans. Presumably that's coming from melting ice, which it is. But you can track how much mass there is because the ocean's also warming up, so it's expanding. So about half of the rise is just the expansion of the water, actually in the surface water, and about half is actually the mass is increasing in the oceans. Now, if you want to be a climate or sea level rise skeptic, you could put your hand over this rapid rise and you could say, nah, it goes up, it goes down. That's about a 5 millimeter drop. And so maybe it's going to turn around and go down. Well, we can actually measure where that water went. And when it went down by 5 millimeters, the GRACE satellite saw the same decrease in the mass, but it saw the increase in the water over Australia and Indonesia. It was massive flooding, and so all that water was sitting on land, and of course, if it's on land, it's going to drain through rivers, that water cycle again, into the ocean, and it all came back right up to the trend line. So it actually closes. It's pretty amazing that that works. Now, we can also measure mass in ice. We do fly over Ice Cube, and if you look at Greenland mass of ice over time, we're losing a lot of ice. It's kind of a scary thing, and it's hard to see in these plots, but you can see the annual cycles, but we're losing a lot of ice in Greenland, we're losing a lot of ice in the West Antarctic ice sheet, Himalayas, all over the globe, and we can measure that. Now, we can also measure water underground. And so this is the Central Valley of California. You don't see it above, although we're actually measuring the subsidence with laser altimetry of the Central Valley. But this is the cumulative groundwater in California's Central Valley from 1962 to 2014 by a variety of methods, including space. and it's not a very pretty story. I don't think I have to tell you about that. Just last month, we launched the Soil Moisture Active Passive. This is a 6-meter radar antenna, and the whole thing spins at 14 RPM, and it's going to make global surface measurements of soil moisture, which is critical for farmers, but also part of this water equation, even though it only accounts surface water for about 0.5% of the overall water balance. So my conclusion on this is that, and here's that thin atmosphere that's the source of those neutrinos again, and here's the neutrino actual detector volume for conversion. But this is from the National Polar Partnership, the SUMI, University of Wisconsin-Madison atmospheric physicist, earth scientist, in partnership with NOAA. Earth science is not only really challenging and interesting, but it's also incredibly important. If you just want some evidence of that and you want to know what's happening where you live, the U.S. National Climate Assessment was just released, and the highlights is a little thin volume. The executive summary is about 300 pages, and I have no idea how big the full volume is, but I'd recommend either the highlights or the executive summary. Now, in the rest of the solar system, of course, you're all familiar with Curiosity. I thought I'd just spend a couple of minutes to tell you some of the exciting things we've been learning. The first is the Curiosity's level 1 requirement, that's NASA speak for why did we send it, was to find out if Mars was ever habitable. Did it have a habitable environment? This was about $2.5 billion. We sent it there. It had a crazy entry, descent, and landing through the Martian atmosphere, 7 minutes of terror. Came down on this sky crane, lowered down, a look of shock on everybody's face that it actually worked, and then we started roving, and from the very start, we found out that, in fact, Mars, about 3.5 billion years ago, and this is the first time we've actually dated a climate on another planet, about 3.5, 4 billion years ago, Mars was wet, there was fresh water, there were rivers, river deltas, lakes. Those lakes were there for hundreds of millions, if not perhaps even a billion years. We don't know that yet, but it was a happening place. It had its own hydrologic cycle. It has probably snow-capped peaks, clouds, rain. It was warm, and it was like that for millions of years, at about the same time that life originated on Earth. So there were almost certainly organics delivered from the late heavy bombardment of early solar system material. It was warm, it was wet, it had the same conditions on which life started on Earth. Did life start on Mars? That's not what this rover was supposed to answer. It was supposed to find out, was it ever habitable? And in the first few days, we found that out. So since then, it's been roving and looking in greater detail, trying to see if it can detect signs of organics. And in fact, recently, we announced that it has seen some chlorobenzene compounds. There are perchlorates in the soil as well, so in the analysis, it'll chlorinate any organics. But this rock that we've been grinding up, this mudstone, and putting into mass spectroscopy, has been sitting there for 3.5 billion years, bombarded by cosmic rays. And so it's not very likely that you're going to see organics unless they're really there. And we see a very strong signal of these chlorobenzenes. Not everywhere, but in this particular mudstone in an area called Cumberland. You know, people name everything that they see. And so this is really interesting. But we also, early on, didn't see signs of methane. And now, as we're driving along, we've recently seen signs of methane. Now, where can methane come from? Well, it can come from geologic processes like volcanism. We've thought that Mars is, being so small, it's cooled off, probably doesn't have the kind of volcanism and plate tectonics we have on Earth, but we know it because we see volcanoes on the surface that it did billions of years ago. Maybe there's a little remnant magma and volatiles and hot water underneath that's creating this methane, or it could be that there was life on Mars and it still is. We actually know that there's wet places on Mars still because we see it seeping out of crater walls. There was an Earth detection of methane from ground-based telescopes, Mum et al. So we were surprised because of the Earth-based detection when we didn't see any. But as we've been driving along, the sol is one Martian day. As we've been driving along, we saw a little hint of a signal and then a definitive signal during the daytime, during the summer. So we think that there's a good chance that there are local sources of methane. This is very interesting. We still don't know what that's from. We may be able to find out with the next rover. We also see nitrogen. So what do I think is important about Mars in terms of the question of are we alone? You need all the components if you think it's life like Earth that could have been there in the past or could be there now. You need various things. You need oxygen, you need carbon, you need nitrogen, so we've seen those. You probably need phosphorus. So we're starting to see all of the bits and pieces that could allow Mars to be a truly habitable environment, and we're still looking for that question of, did it harbor life or does it now? Another place that might harbor life in our solar system is the moon Europa of Jupiter. Jupiter is a really nasty place. 2001, A Space Odyssey, got it wrong. The radiation environment is way too bad to go there. The movie, not the book. But Europa is an interesting place because first of all, you don't see a lot of craters. This is a very young surface, 50 million years old. It's all ice. This would make a great neutrino detector, no doubt. Except for all this brown stuff. This brown stuff, we have no idea what it is. Everything we know about Europa comes from 11 flybys of the Galileo spacecraft more than a decade ago and a few Hubble observations. But we believe that it has this roughly 5 to 30 kilometers thick ice shell and then a thick ocean, more salty water than on Earth, more water than is on Earth, and it's been like that for 4 billion years. So you have this warm, salty ocean protected from the radiation for 4 billion years, and probably geologic activity like hydrothermal vents, and that's because of the tidal heating by Jupiter. Jupiter's a really big, nasty mass, and it's been like that for 4 billion years. Has life started there? Well, we don't know. We are going to send a mission. We're starting this year with our budget submission, the plan to start a mission to Europa, and Hubble has seen evidence of plumes. This is ionized hydrogen, ionized oxygen signal from Hubble down here as well, 200 kilometers tall. Europa is big enough that that water will come out and then land back on Europa. And so we're hoping to map out, do optical spectroscopy of this orange gunk, brown gunk, find out what it is, measure the thickness of the ice, and maybe fly something through the plumes, sample it, and see if we can see any signs of life. Of course, that's going to be probably a decade away or more, but very exciting thing to do. Now, in astrophysics, we have many missions that you're familiar with: the Hubble Space Telescope, the Spitzer Space Telescope, the Chandra X-ray Observatory that's not up here. But these are our great observatories, and this was a big leap for science to fund very expensive, very general-purpose observatories and then see what we learn. And there were specific objectives, but it was a grand plan. We're trying to continue that plan, some at small scale, some at bigger scale. The Transiting Exoplanet Survey Satellite is going to do what Kepler has done in this one deep field to look for the blinking of starlight indicating planetary systems, but for all the nearest stars. We want to know where are all our neighbor planets, not just this one field. When Kepler was launched, we didn't know whether it would find any. Of course, Bill Barucki, the principal investigator, really knew we would, and in fact, we have thousands and thousands of planetary systems. The Transiting Exoplanet Survey Satellite will launch in 2017. In 2018, we'll launch the James Webb Space Telescope. James Webb was the second administrator of NASA, and so you think, why are we naming a great observatory after an administrator? But he was also the guy that put science in NASA, really cemented the basic science research in NASA that we all benefit from. So I think that's appropriate. In the 2010 Decadal Survey, the Wide Field Infrared Space Telescope was proposed. Since then, we got some very nice telescopes from the National Reconnaissance Office. So we've called it the Astrophysics Focused Telescope Asset. We're hoping to be able to get started next year on doing that. Hubble and James Webb Space Telescope are very narrow field of view, very deep. The Wide Field Infrared Space Telescope will be very broad, looking for weak lensing, gravitational lensing, for dark energy, also dark matter. However, if we want to answer the question, are we alone in the universe, it's probably going to take something bigger than James Webb, and I'll talk about that a little bit later. James Webb Space Telescope is 6.5 meters, and you just need to collect a lot of photons if you want to get a spectrum of an Earth. And Earth around a nearby star, say 25 light years away, is dimmer than the dimmest galaxy in the Hubble deepest field. So it's a hard problem. And it's right next to a star that's 10 billion times brighter than the planet in reflected light. So I couldn't give a talk unless I talk about the Hubble Space Telescope, especially since this is the 25th anniversary of the Hubble Space Telescope on orbit this April. One of the reasons Hubble is so powerful is because it has that longevity. The other is it's above the atmosphere, very stable, great optics. But even more important, we've been able to upgrade it with new instruments so it keeps up with the latest state-of-the-art detectors. And that's my spacewalking partner, Drew, physicist, and myself, as well on the side of the telescope in 2009. Now again, Hubble was built with some primary objectives. Measure the extragalactic distance scale and measure the Hubble constant locally. That was the goal. Measure quasar absorption lines, try and map out some of the history of the universe. Look at the origin and evolution of our own solar system. Look at supernovae and try and figure out what's going on there. A few other things. But what's really remarkable about Hubble is all the things that it discovered because our imagination wasn't that great, but more so because the universe is much more interesting than we ever expected. Sources of gamma ray bursts. We've determined they were extragalactic. We didn't know that before we launched Hubble. And that they're sources neutrinos. Back to Francis' talk. The age of the universe. We've actually been able to very accurately measure the age of the universe. We've validated that there are supermass holes. And first of all, we've proved the existence of mass holes and then validated that at the center of nearly every galaxy is a supermassive black hole. Something we really never imagined until this last servicing mission when we put in the Wide Field Camera 3, that we'd be able to look at individual stars in the nearest galaxy, Andromeda, and measure the stellar ages in another galaxy. Another thing, when Hubble was launched, as I mentioned, we didn't know about any other planets in the universe. Hubble has done spectroscopy of atmospheres of planets around nearby stars, as has the Spitzer telescope. And of course, gravitational lensing, dark matter, acceleration of the universe, and dark energy. So these charts are thanks to Adam Rees, but Hubble looked at these stars called Cepheid variables, and they have the property that their pulsation rate is proportional to the luminosity. And so this is an example of a Cepheid variable. And because they're kind of standard candle then, you can measure the distance to galaxies where you can see these Cepheid variables. And that's what Hubble did, and of course discovered that on average, most galaxies are moving away from us. And as a freshman at MIT, I did work with Ken Brescher, who's in the second row here, actually trying to reproduce Hubble's results, because it's not a linear law, he guessed. There's selection effects, the Malmquist effect, and I used a luminosity function for galaxies, and on my little hand calculator integrated the functions to figure out what he should have seen. But anyway, so it's fun to sort of be back doing this work. But when Hubble was launched, Wendy Friedman and others had a core, here's Hubble's original data, a core project to try and measure the Hubble constant. And we got out pretty far, and we're able to make the best measurement ever of the Hubble constant to a precision of about 10%. Well, remember, Hubble looks at this tiny little soda straw view of the universe, but in that view are thousands of galaxies, which means we get lots and lots of supernovae. We sample a huge volume of the universe. So this is an example of before this is a galaxy. I know it looks just like a tadpole. Before the supernova, after. Before, after. This one actually kind of looks like a galaxy. Before the supernova, and it's red because it's much further away, after. And this is with the advanced camera for surveys. And we've been able to get out to a redshift about 1.34, which is about 9 billion light years. So because we've been able to do these servicing missions, put in new cameras, new capability, more sensitive, more red, we've been able to move the bar further and further out to measure the Hubble constant. And of course, as you know, it's not a straight line. It varies. And that led to the conclusion that the universe is accelerating, at least for the last 6 billion years. And Adam Rees, Brian Schmidt, and Saul Perlmutter won the Nobel Prize for the accelerating universe, the conclusion of which is this dark energy. And so no Hubble, no Nobel Prize is what Adam says. So I figure it was worth risking my life for. It's kind of a cool thing. Now, we're also able to extend that with Hubble to look at other ways of measuring the universe. And in this case, looking at megamasers and galaxies, which give you whose speed and centripetal acceleration is known, allowing you to figure the distance to the galaxies. And so what Adam and team are doing now is to try and build an extragalactic distance scale ladder, anchoring Cepheids to these other mechanisms, along with the Wilkinson microwave anisotropy probe work, to try and get down to, well, he's currently at about 3.4% error in that Hubble constant. He's trying to get even much lower. Now, why do we care about that? Well, because it's linked to other fundamental physics, and in particular, dark energy. Now, I'm not convinced that measuring the Hubble constant over time or weak lensing will allow us to figure out what dark energy is, but it's about all we have to go on right now. And it's amazing that from the measurement of the Hubble constant, you're able to constrain various interesting things. like the equation of state of dark matter, into a very narrow range, 1.08 plus or minus 0.1, which is pretty darn close to 1, but it has this long ellipse. So right now we're in this narrow range here. The sum of the neutrino mass to a fraction of an EV. Also very interesting, the number of neutrino species. And I'm just fascinated by the fact that the centroid is about 4, but of course, we'll have to see. We think we may be able to get down to 1% precision on the Hubble constant, which will bring you down to a much smaller area. Now, I mentioned the Kepler Space Telescope staring at this region of space near the constellation Cygnus. The reason it's looking there is because there's lots of stars. They wanted the highest probability they could get that they would see these little tiny dips as a planet eclipsed the star. And of course, now we've seen thousands and thousands of planets. Really amazing. Many of which are rocky, many of which are in the zone where liquid water exists, the so-called habitable zone. So we're very excited about that. Now, if you look at our solar system, the assumption was that most solar systems, if they existed, would have lots of Jupiters, Neptunes, Uranuses. And in fact, those heavier planets turn out to be rare. Our solar system may be a little bit unique, and there's lots of super Earths, meaning more massive than the Earth, or higher radius than the Earth, up to sort of mini Neptunes, mini Uranuses, and lots of small ones as well. So really incredible that we've been able to see that. Test will find all the local ones, and then hopefully we can bring the power of the James Webb Space Telescope, launching October 2018, going where no Hubble has gone before. Because it's an infrared telescope, it's going to be able to see deeper. In the Hubble Deep Field, we basically run out of galaxies, and there's 2 reasons. The main one being that because of the expansion of the universe, the light is redshifted out of the band of Hubble. But until we look, we don't know. Maybe we run out of galaxies. Maybe all our theories are wrong. I'm convinced James Webb Space Telescope, by seeing deeper, is going to reveal that population of baby galaxies, see the first generation of stars and galaxies and the evolution as we come out of this dark age of the universe. And so it's going to hopefully see the very first light as we come out of reionization of the universe, sometime around 100 million years after the Big Bang. We're also going to be able to look in detail at the planetary disk and planets around nearby stars, the assembly of galaxies, the birth of stars and planets, with this infrared capability that can see through the cosmic dust. Right now, Hubble sees these beautiful nebula, but what we're really seeing is the outside envelope of the dust, and we can't see the stars and planets being formed inside. The James Webb Space Telescope is essentially a spectroscopic observatory, and that's the huge advance that we're going to make, in addition to the fact that it has 100 times the light collecting power. And just because of lambda over d at 6 meters, it's going to produce sharper images than Hubble. But we're going to be able to do transit spectroscopy of planetary atmospheres and hopefully look for features like water features, carbon dioxide features. Every image is going to be a data cube of imagery and spectroscopy. And we're going to try and see back to those very first stars and galaxies. So I'm very excited about the James Webb Space Telescope. This is a simulation of what we might be able to see on a super Earth. We won't be able to get down to Earths because they're too close to the host star and too small a signal. But at 15 or 45 light years, 15 is the black line, 45 is the green line, we're getting reasonable statistical significance on. And this shows a water line and a methane line in an atmosphere of a rocky planet around a nearby star. Now, I mentioned the Wide Field Infrared Space Telescope. We're hoping this year to get started on that, pending approval of the administration and of Congress. We're already pretty far ahead in that we have the optics. We've put together a science definition team. We've done cost studies, all of which have confirmed that it makes sense to go forward. It's also going to give us, instead of this narrow view, a very wide view, so we can look at the structure of the universe, to do weak lensing, to do correlations, try and get a handle on the dark energy. It's also going to do a lot with exoplanets, because we're going to start to see micro-lensing events where planets are lensed by nearby star systems or massive stars. We're going to put a coronagraph that hopefully will allow us to directly image planets up to about 10 to the 9 contrast ratio, 1 billion times dimmer than the nearby star. And of course, all of general astrophysics. Just to give you an example, well, let me go to the next slide. We all love the Hubble deep field images, and I'm sure many of you have them on the walls of either your office or at your university or research lab. They make great screensavers. 5,000 galaxies in one image. It's mind-bending. And because of that, because it's a tiny soda straw and we have a few of them, we know there's about 200 billion galaxies in the universe. We're actually able to count them. Here's what the wide field camera on the Wide Field Infrared Survey Telescope will be able to do in one image, 1 million galaxies, with the resolution of Hubble. Pretty amazing. Now, I'd be remiss if I didn't talk about the International Space Station and specifically the alpha magnetic spectrometer on the International Space Station. Here it is. This is a conventional magnet, but it's an amazing cosmic ray detector that Sam Ting and dozens of other countries put up. And this is a Soyuz capsule. That's a Progress capsule. This is the Russian segment, the US Truss. The International Space Station is just an incredible collaboration of countries around the world that are current, or were foes. And I think it's around science that we really come together. And Sam Ting is a master of that. Next week, he has a conference to talk about results. This is a detailed view of it. It's been up there for a number of years, collecting cosmic rays. It's already done the best job of conventional low energy. And as a cosmic ray physicist myself, up to a TeV and below is low energy. But it's really nailed the cosmic ray spectrum of hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, silicon, magnesium, all the way up to iron, better than all the experiments prior. What Sam is really interested in is, can he detect dark matter annihilation. So next week, I was hoping I'd be able to get some sneak preview and bring it here, but this is previous work from last year. This is the spectrum, this is the positron fraction, positrons over the sum of positrons plus electrons. And I don't want to spend too much time, but we know what the collision of cosmic rays produce. Francis gave us a great account of that. This is the observed spectrum, and the interpretation, it could be from a collection of pulsars. Sam's favorite is it could be dark matter. We'll have to see. So this is next slide. This slide is a very dangerous slide because what I did at 2:42 a.m. this morning was just start typing the names of missions that we either have or are coming up in the near future, both in space and on the ground. And so if you don't see your favorite telescope or mission here, I apologize. But it's just to point out that we are about to enter what I think will be the most amazing phase of physics and astrophysics ever. And that's in a really tough funding environment. But we have the Hubble. We're about to have the James Webb Space Telescope. Hopefully the Wide Field Infrared Space Telescope. On the ground, the 30-meter telescope, the Giant Magellan Telescope, the extremely large telescope. We have ALMA, which is just making amazing strides. And the thing about ALMA, Hubble, and James Webb Space Telescope is they have about the same resolution on the sky. And one of the things that's transformative about telescopes like that, and it'll be true for TMT and GMT and ELT as well, is that we finally built instruments that have about the same resolution as the human eyeball. And I think that's why the images from Hubble have resonated so well with the public. Even if they don't know the physics, they know the beauty of the universe. And as we as scientists describe that beauty to them, it makes a big difference. And so many, many different missions, looking for life in the universe, looking for the origin and evolution of the universe, trying to unravel the mysteries of the universe is what we're all about. And so I just want to give you the plea that, make sure as you do this exciting science that you go out and communicate it with your family, number one. They're the ones that make big sacrifices to enable you to do the work. Your community, local schools, and as the slide said, whether you're a fan or you're not a fan of basic research, talk to Congress, because they're big decision makers. We have a panel to talk about that a little bit later. Thank you very much.